Thanks, Shannon. And hey, everyone. Thanks for joining today's session, Smarter Phosphorus Monitoring, Success Stories from Wisconsin Water Resource Recovery Facilities. I'm Adrienne Stenz, Application Development Engineer for YSI, and I specialize in process optimization using online instrumentation. Today, I'll be taking you through the science behind phosphorus, the tools we use to monitor it, and how real utilities in Wisconsin are using online phosphorus analyzers to improve their operations. Let's start off by talking about why phosphorus monitoring matters. Phosphorus is one of life's essential elements. It's found in our DNA, in our cells, and in our bones. But in excess, it becomes one of the most harmful pollutants for our waterways, specifically for freshwater systems. Wisconsin is a hot spot for phosphorus concerns due to its combination of agricultural runoff and high quantity of freshwater lakes, resulting in strict phosphorus effluent limits for facilities. That's why smarter phosphorus monitoring is so important. It gives utilities real-time visibility and control into this essential parameter. So let's take a step back and talk about what phosphorus actually is and how it behaves in the environment and in our treatment systems. Phosphorus is essential to life on Earth. All living beings are made up of 6 main elements. Those elements are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Now, phosphorus exists in nature in the form of phosphates, where one phosphorus molecule is bound to 4 oxygen molecules, or PO4. I wanted to bring this up because the two terms, phosphorus and phosphate, are used interchangeably because phosphorus exists naturally as phosphate. Phosphorus is an element that by itself is extremely reactive, so PO4 is its most energetically favorable state. So whenever we're talking about phosphorus, we're really talking about phosphate. Orthophosphate is another popular term that's used when talking about phosphorus. Orthophosphate refers to a single phosphate group by itself. When a single phosphate group is on its own, then it carries a negative charge of -3. Now, phosphates make up the backbone of all living things. Like I said, they're one of 6 main elements needed for life on Earth. They're responsible for cellular energy. So if you remember from chemistry class, ATP is the compound that gives our cells energies. ATP stands for adenosine triphosphate. Bones and teeth are also primarily made up of calcium phosphate, so phosphates make up our entire skeleton. And last but certainly not least, phosphates are in DNA. The spiral backbone of DNA is made up of a phosphate group bound to a sugar group. And then these bridges are nucleic acids, A, T, G, and C. So they make up the entire backbone of DNA. So phosphates are within us, and an excess of phosphates in our system gets discharged with our waste. When plants and animals die, they decompose in the soil, and the phosphates from their bodies return to the soil, all part of the natural phosphorus cycle on Earth. So phosphorus is essential to life, but an excess of it can be super harmful to the environment. You probably heard about harmful algae blooms. These are driven by a phenomena called eutrophication. Eutrophication is essentially a state where the water body is maxed out on the amount of nutrients it can have, allowing algae to grow uncontrollably. These algae blooms can be super harmful. They block sunlight from the water, creating oxygen dead zones that lead to large-scale fish kills. Phosphorus is the limiting nutrient in freshwater systems. So that means when there's an excess of phosphorus in fresh water, the potential for eutrophication to occur is high. Sources of excess phosphorus that make its way back into our waterways mainly come from agricultural fertilizer runoff. Nitrogen and phosphorus are concentrated into fertilizer pellets, which make their way back into the waterways at concentrated levels. Wastewater resource recovery facilities are also considered point sources for nutrients like phosphorus. Since we all discharge it from our bodies, it gets concentrated at a wastewater facility before it gets discharged into the environment. So let's talk a little bit about the history of phosphorus effluent limits for wastewater facilities. It all started in the late 60s when, in 1969, the Cuyahoga River in Ohio made headlines for catching on fire, not for the first time, but for the second. So at that time, total phosphorus concentrations in our nation's waterways were around 11 milligrams per liter. So this brought the nation's attention to the state of our waterways and led to the 1972 Clean Water Act, which just celebrated its 50-year anniversary in 2022. The Clean Water Act spent about $350 billion in improving wastewater facilities and implementing NPDES, or National Pollution Discharge Elimination Society limits, to reduce the amount of nutrients like nitrogen and phosphorus that were getting discharged into our waterways in an effort to clean up our nation's water. By 2010, select states and facilities that discharged into impaired waterways had select phosphorus effluent limits. States like Wisconsin, which has a lot of farming and a lot of freshwater lakes, had implemented statewide phosphorus limits by this time to protect their water resources from eutrophication. And today, phosphorus still remains a key nutrient of concern for our nation's waterways. The National Lake Assessment from the EPA had reported in 2022 that across the country, 50% of our lakes were in poor condition due to elevated phosphorus levels. So wastewater facilities are still on the hook and have pressure to discharge as little phosphorus as possible back into the environment, with certain Great Lake regions now targeting ultra-low TP limits of less than 0.1. All right, now we're going to do a quick poll question. So Shannon, if you could put this up. What are the current phosphorus limits for your facility if you do work at a wastewater facility? Are they greater than 1 milligram per liter, between 0.5 to 1 milligram per liter, less than 0.5 milligrams per liter? Do you not have a phosphorus limit, or is it not applicable to you?
We've got several responses coming in here. I'll give you just a few seconds. Okay, so let's see if I can share the results here.
Nice. Okay, so it seems like the majority of people not applicable, or between 0.5 to 1 milligram per liter phosphorus, which is great because this presentation is going to be really applicable for you. Cool. All right, when we talk about phosphorus in wastewater, we're talking about a few different forms of it. All of these forms are phosphates. In wastewater, phosphorus can be soluble or particulate. Soluble means dissolved in water. Particulate means attached to solids. Colloidal is an intermediate stage between particulate and soluble. Typically, influent wastewater is half soluble, half particulate phosphorus. Now, total phosphorus is the NPDES compliance measurement and is testing for all of these forms of phosphorus in a wastewater sample. When we talk about orthophosphate, we're only referring to soluble reactive phosphorus in a sample. Reactive is a method-based chemistry term for orthophosphate. So if you remember from a couple slides ago, Orthophosphate is a single phosphate group by itself, meaning that it's readily available for chemical and biological reactions, hence the term reactive. Now, total phosphorus is the compliance measurement, but orthophosphate is a good measure of process efficiency. It's what remains in your solution after all of the particulate matter has been removed. So you can think of orthophosphate as the phosphorus that's still floating around freely in the water. If your plant is removing phosphorus well, then the amount of orthophosphate should also be low. By tracking orthophosphate in real time, you can see how efficient your removal process is and adjust it if needed. It's kind of like checking the fuel efficiency while driving. You get a live indication of how well your system's running. All right, now that we know a little bit about phosphorus, phosphate, and the forms of it in wastewater, let's talk about how it gets removed. So there are three main strategies for removing phosphorus from wastewater, all of which target soluble phosphorus in the water to turn it into particulate phosphorus that can then be settled out in secondary clarifiers. The first option for removing phosphorus from wastewater is chemical removal. This is the most popular and common option due to how long this kind of technology has been around. Chemical removal involves dosing chemicals like ferric or alum to bind phosphorus in the water and later get settled out. The second way to remove phosphorus from wastewater is biologically in a process called enhanced biological removal, or enhanced biological phosphorus removal, EBPR, which is a more recent innovation but becoming increasingly more common. Biological phosphorus removal involves having a dedicated zero oxygen anaerobic zone in your biological treatment process to grow select microorganisms that will remove phosphorus from the water for you. And then the third option to remove phosphorus from wastewater is tertiary filtration. This is the least common option, and these are often used for effluent polishing to meet ultra-low limits of phosphorus. So we're going to go through each of these strategies briefly, just to talk about how they work. Starting with chemical removal, which is the most common option. Chemical removal works by dosing metal salts into wastewater. These metal salts are usually either iron or aluminum based because these metals have a high affinity for phosphate. When these metal salts enter the water, they form something called hydrous metal oxides, or HMOs. Now, these HMOs are positively charged because metals are positively charged, and so they attract negatively charged phosphate in the water to absorb to their external surface. They also have a complex enough surface area that they can enmesh and capture particulate phosphorus as well. The metal ions react with phosphate to form an insoluble metal phosphate precipitate that can then be removed via secondary clarifiers. Dosing of these HMOs typically occurs in aeration basins or sometimes in primary clarifiers, anywhere upstream of secondary clarification. So what exactly are these HMOs? This image shows a ferric chloride HMO under an electron microscope. So you can see the complex surface it has, which creates many binding sites for soluble phosphorus and increases its ability to capture particulate phosphorus. These HMOs can be produced by a number of different metal salt flocculants. Like I said, most of them are aluminum or iron-based. Aluminum sulfate and ferric chloride are the most common, earning them the nicknames alum and ferric. And nowadays, some plants are testing rare earth minerals like lanthanum and cerium for chemical phosphorus removal. These rare earth minerals are supposed to form denser, faster settling precipitates. However, at the time, they are more expensive, and not readily available. So chemical phosphorus removal is well established. It's a pretty quick process and it's very effective. It's also probably the easiest strategy to implement out of all three phosphorus removal strategies. The downside of chemical phosphorus removal is that it creates a lot of chemical sludge that you have to get rid of. The more metal salts you dose, the more sludge you create that you have to dispose of. Additionally, it's expensive to go through these chemicals. All right, let's move on to the second strategy for phosphorus removal, which is enhanced biological phosphorus removal, EPBR. EPBR involves creating the right biological conditions for select microbacteria that remove phosphorus from the water. These bacteria are called PAOs, or phosphorus accumulating organisms. These PAOs require alternating anaerobic, so zero oxygen, and aerobic, oxygenated conditions to remove phosphorus from wastewater. These PAOs store phosphorus inside of their cells, and they require carbon as a food source for energy. The way that these PAOs remove phosphorus is a two-step process. The first step occurs under anaerobic conditions with no oxygen. PAOs store their carbon food source before eating it, kind of like putting a snack in their pocket for later. When they do this, they release all of the phosphorus that is stored inside of their cells into the water. The second step occurs when the PAOs enter an aerobic zone with oxygen. The PAOs finally consume their carbon food using oxygen. When they do this, they uptake phosphorus out of the water and back into their cells, accumulating more phosphorus than they had released in the anaerobic zone. So this excess phosphate uptake by PAOs in the aerobic zone is what makes BioP an effective process. These PAOs are then settled out in secondary clarifiers, taking the phosphorus stored inside their cells with them. Now, the success of EBPR systems rely on a few things. First, the PAOs must have enough food, which their food is a specific type of carbon, or BOD, called volatile fatty acids. Therefore, you have to have a sufficient supply of carbon for biological phosphorus removal. Sometimes this requires an external source of carbon, especially if you're trying to remove nitrogen from your process as well, because nitrogen removal requires a lot of carbon as well. Simple methods for monitoring volatile fatty acids don't exist. However, online monitoring of COD and BOD is possible with a spectral sensor like shown here. And that can be beneficial if you are dosing external carbon to optimize the use of carbon that's in the wastewater and minimize the use of external carbon. Additionally, the integrity of an anaerobic zone is really important for biological phosphorus removal. Anaerobic means zero oxygen, so that means there should be no dissolved oxygen and no nitrate present, since nitrate has oxygen bound inside of it. That's why anaerobic zones are always at the front of treatment trains so that no DO gets in them. But you still have to be careful with RAS or MLR lines that are bringing carryover nitrate back into that zone. ORP is a really useful parameter for anaerobic conditions to verify that those conditions are truly anaerobic. ORP values for anaerobic zones should be largely negative, less than negative 100 millivolts. And then finally, EBPR processes require efficient secondary clarifiers to prevent captured particulate phosphorus from escaping to the effluent. The phosphorus content of EBPR sludge can be 10% by mass or higher. So continuous monitoring of effluent TSS from secondary clarifiers can provide an early indication of upsets of that and provide a signal to start polymer addition, for example. Additionally, secondary release of phosphorus can occur in a secondary clarifier if you have a really deep final settling tank and the bottom of the mixed liquor becomes anaerobic, signaling those PAOs to release the phosphorus from their cells. So minimizing your sludge blanket depth can prevent that secondary release of P in final settling tanks. Phosphorus can then be removed from sludge handling by chemical treatment or by installing a struvite recovery system. And the final option for removing phosphorus from wastewater is tertiary filtration. This is the least common phosphorus removal strategy and typically serves as a polishing step. You'll see tertiary filters deployed when a facility needs to meet ultra-low effluent limits. We're talking total phosphorus and total nitrogen less than 0.1 milligram per liter, and total suspended solids less than 10. Tertiary filtration comes after secondary clarification, and it works by physically removing remaining solids, including any particulate phosphorus and any flocks that didn't settle out in a clarifier. There's a couple of filtration types used in wastewater. One is a rapid gravity filter. These filters are layered media, often sand and activated carbon, that allow water to flow downward through those layers by gravity. As water flows, the media captures fine particles and phosphorus bound to solids. Some systems even incorporate chemical dosings right before filtration to enhance phosphorus removal via filtration. Another option is a rotating disc filter. This is a mechanical filtration system made up of multiple vertical filter panels arranged like slices of a pie. As water passes through, solids are retained on the surface of these discs and clean water moves through to the effluent. Over time, these discs rotate and are periodically backwashed to remove accumulated solids. All right, that brings us to our next poll question. If you work at a utility or facility, which phosphorus removal strategy do you rely on if you are doing phosphorus removal? Is it biological, chemical? Do you have tertiary filtration? Are you doing some combination of these three or not applicable?
A few responses coming in. Thank you all for your participation. Okay, let me share the results here.
Okay, nice. So it looks like majority of people that are doing phosphorus removal are doing some kind of combination of these three strategies or relying mainly on chemical phosphorus removal. It's good to know. So where does phosphorus monitoring fit in? Online analyzers can play a critical role across all three phosphorus removal strategies: chemical, biological, and tertiary. And this is a diagram of a wastewater treatment plant showing the various stages of the process. So for chemical phosphorus removal, analyzers are commonly installed at the final effluent of a plant or at the effluent of an aeration basin. These positions allow for real-time feedback control of chemical dosing, ensuring that ferric or alum is added only when necessary to meet your phosphorus loads. These same locations, plant effluent or aeration effluent, are also effective for monitoring biological phosphorus removal. They allow operators to verify that PAOs are functioning properly and that soluble phosphorus is being fully converted into biomass and removed through settling. When EBPR is working well, orthophosphate levels at these points should be minimal. And for facilities using tertiary filtration, which isn't really shown on this diagram, online analyzers can monitor phosphorus both before and after tertiary filters, helping quantify how effective that filter is at removing phosphorus and ensuring that ultra-low limits are consistently met. The YSI Alyza orthophosphate analyzer can detect phosphorus concentrations as low as 0.02 milligrams per liter orthophosphate, making them ideal for plants with really tight effluent limits. All right, now that we know how phosphorus is removed from wastewater, let's talk a little bit about online analyzers for phosphorus. Starting with the difference between testing for orthophosphate and testing for total phosphorus. Orthophosphate, which is a single phosphate group by itself, is the only form of phosphorus that we can directly measure. That means if you want to measure total phosphorus in a sample, which includes all forms of phosphorus, you first have to convert everything into orthophosphate. This is done through acid digestion, a process that breaks down all the other forms of phosphorus into orthophosphate. Once that conversion is complete, you can measure the total amount of phosphorus in the sample by colorimetrically measuring the orthophosphate concentration. The disadvantage for total phosphorus testing is that this digestion process takes time and requires strong reagents. Now, testing only for orthophosphate involves taking a filtered wastewater sample and measuring orthophosphate via the same colorimetric measurement method. This is an instant measurement that provides insight into the amount of reactive phosphorus in your system. So there are two colorimetric measurement methods for determining orthophosphate, the yellow method and the blue method. The yellow method, or molybdenate method, features a single reagent, which is a mixture of ammonium molybdenate and vanadium in the presence of an acid. When orthophosphate is present in your wastewater sample, it reacts with the molybdenate and acid medium to form a complex. The vanadium in that reagent then reacts with this complex, forming a resulting compound that's a yellow color. The intensity of this color is directly proportional to the amount of orthophosphate in your sample. So that yellow color is then pushed to a spectrophotometer to measure the absorbance at a specific wavelength and convert it into an orthophosphate concentration. With the higher the absorbance, the higher the orthophosphate concentration. This yellow method has a limit of detection of 0.02 milligrams per liter orthophosphate. The blue method follows the same mechanism, but involves an additional reagent of absorbic acid. The absorbic acid reagent turns the sample blue instead of yellow, and the blue method has a lower limit of detection than the yellow method and is the compliance standard. Online analyzers like the Alyza IQ use the yellow method to determine orthophosphate concentrations. And these are the main components of online orthophosphate analyzers. These are the sample pumps. So these are connected to a 0.45 micron filter, which is sitting in your process. And these are drawing sample into the analyzer. This analyzer has two sample pumps, so it can analyze two streams, but others might have one. The pump pulls sample into an overflow vessel so that sample is always readily available to be mixed with reagents. The sample gets mixed with reagents in a little mixing valve that's behind this steel cover plate. And this is where those reagents hang in the back of the analyzer. Once the sample gets mixed with reagents, it gets pushed to a photometer that's behind this housed styrofoam measuring unit to analyze the absorbance and spit out a concentration. The things you can't see here are the intake and drain lines, the power lines, and communication. So these can communicate to SCADA via 4 to 20 milliamp, Ethernet, or Modbus or Profibus. In terms of maintenance for online analyzers, these are the things that you have to do. This is the 0.45 micron filter that gets installed in the process that the analyzer pulls sample up through. Depending on where this is installed in your process, depends on the cleaning frequency. So if the analyzer is at the effluent facility, then you might not have to clean this filter until every 4 weeks. But the further upstream you move the analyzer, the more frequent cleaning is required for this filter. This filter also gets replaced about once a year. The main consumables for an orthophosphate analyzer are the reagents. The reagents have to be replaced every 3 months when operating at the minimum 5-minute measuring interval. The measuring interval is user selectable from 5 to 60 minutes. So the longer you set it, the longer your lifetime of reagents will last. In addition to reagents, there are also calibration standards that hang in this analyzer that are set to automatically calibrate these units daily. And there's also cleaning solutions that hang in the back of this analyzer that are set to clean the internal lines of the analyzer daily. So those calibration standards and cleaning solutions have to be replaced about every 6 months. And then this is the little mixing valve where sample gets mixed with reagents. This mixing valve has to be replaced about every 6 months as well. Though they require maintenance, online analyzers for phosphorus often pay off when compared to grab sampling and laboratory testing. Grab samples are snapshots in time, which only give you information in that specific moment, versus online instruments give you access to data 24/7, with which you can make informed decisions immediately and not after you wait for lab results to come back. Facilities that implement online analyzers to automate chemical dosing for phosphorus removal allow themselves to optimize that process, which more often than not leads to reduced chemical use, leads to lower chemical costs, and less chemical sludge to dispose of. All right, now let's get into some case studies. We're going to look at 3 plants in Wisconsin that are using online PO4 analyzers to monitor and control their phosphorus removal strategies. Let's start with Oconomowoc Wastewater Treatment Facility. Oconomowoc is a mid-sized utility that averages about 2.4 mgd and has an effluent total phosphorus limit of 0.95 milligrams per liter. To meet their phosphorus limit, Oconomowoc uses chemical phosphorus removal, and they're also part of a sustainable watershed protection program, which I'll touch on in a few slides. Oconomowoc installed the Alyza analyzer in 2020 at the effluent of their facility indoors in their disinfection building to automate chemical dosing of ferric chloride upstream. The reason that Oconomowoc implemented the Alyza analyzer was because of operations manager Kevin Freber and his experience at his previous utility, Watertown Wastewater Treatment Plant. At Watertown, Kevin and his team had implemented the P700 PO4 analyzer, which is the predecessor to the Alyza. They installed that back in 2015, and in doing so, the facility saw a 25% reduction in ferric chloride usage within the first year. So when Kevin moved to Oconomowoc, he took the same proven strategy with him and implemented the upgraded Alyza PO4 analyzer to automate chemical dosing in a similar fashion. The main improvement made when the P700 was upgraded to the Alyza IQ was the measuring unit where that yellow method takes place. The Alyza IQ features a housed measuring unit and this tiny multi-port mixing valve, which mixes small amounts of sample and reagents together, minimizing reagent use and chemical waste. So with this little mixing valve, it uses less than 5 microliters per measurement and leads to less than 1 milliliter per day of chemical waste when operating at a 10-minute measuring interval. Economowalk's analyzer is installed indoors in their disinfection building at the effluent of their treatment process. Chemicals for phosphorus removal are dosed all the way upstream in the aeration basins like shown in this graphic. So this setup allows the analyzer to serve as a compliance check right where it matters, right before discharging into the environment. The analyzer tests for leftover soluble orthophosphate in the system, so it serves as a good control point for how much dosing needs to change upstream. The Alyza analyzer directly controls 2 ferric chloride dosing pumps, shown here. And the pumps use a multi-level control scheme to target an orthophosphate concentration of 0.52 parts per million. The pump speeds vary from a minimum of 20 to 36%. When PO4 rises above 1.5 parts per million in the effluent, the pump speed is adjusted up by 1.5% to increase dosing. And when PO4 levels fall to low levels, below 0.03, then the pump is adjusted at lower levels of 0.5% to fine-tune dosing at the lower concentrations and minimize overdosing chemicals. Since installing the Alyza in 2020, Economowalk has only been out of compliance once for phosphorus. So this is a graph of Alyza PO4 readings in dark blue compared to effluent total phosphorus laboratory samples taken daily in light green from data going back from 2020 through December 2024. You can see that both PO4 and laboratory total phosphorus have stayed in the range of 0.4 to 0.6 for the majority of the last 5 years, hovering right around that 0.52 set point. Even though their limit is 0.95, you can see they stay well below that limit, and you can see how stable the effluent phosphorus levels are throughout the entire 5-year period. So this isn't short-term success, it's stable performance over 5 years, which speaks to the reliability of both the analyzer and the control strategy. You can also see how closely the Alyza PO4 measurements track with the daily laboratory tests for total phosphorus. So this graph shows a linear regression of the Alyza PO4 readings versus daily effluent total phosphorus lab samples with the data we just looked at from 2020 through 2025. A linear regression is a typical way to determine how well of a relationship 2 parameters have to each other. And the resulting R-squared value indicates that. So a good R-squared value for science and research is typically anything above 0.7. You can see the R-squared value for Alyza PO4 versus effluent TP for Economowalk is 0.84. And that's taking 5 years of data into account, which is about 1,800 total phosphorus lab tests. So this goes to show that the Alyza PO4 is a great indication of the effluent total phosphorus levels at this plant. Now, you might be confused because we talked about the different forms of phosphorus in water and how orthophosphate is different than total phosphorus. But it makes sense that these 2 parameters would be analogous because of where the orthophosphate analyzer is located. It's located at the final effluent of their plant. So at this point, all of the particulate phosphorus solids have been removed. So anything that's left over should be that soluble orthophosphate. So it makes sense that these 2 parameters have such a tight correlation since the analyzer is at the final effluent of the plant. This graph shows Alyza PO4 in dark blue, daily laboratory TP in light green, and ferric chloride usage in orange from 2021 through 2024. You can see that the ferric chloride usage trends well with the Alyza and effluent TP levels. So as Alyza detects increases in PO4, the dosing system ramps up, And as PO4 concentrations drop down, the system backs off. And the effluent TP, confirmed through laboratory testing, follows this same pattern closely, showing that the control system is doing its job. Unfortunately, there weren't any logs of ferric usage before 2021, so we couldn't calculate exact chemical savings from the analyzer, but we do see that this system is highly responsive and that the dosing pumps are reacting in near real time to the actual process conditions. One of the most inspiring aspects about Economilloc wastewater treatment facility is that they're not just focused on their plants discharged, they're thinking holistically about their whole watershed's health. Economilloc is a founding member of the Economilloc Watershed Protection Program, or OWPP. This is a collaborative initiative that's aimed at reducing phosphorus and improving water quality across their entire watershed. This program includes a range of impactful strategies such as conservation agriculture, like cover cropping, filter strips, and low-impact tillage. It also includes stormwater improvements like aggressive street sweeping, leaf collection programs, and rain garden programs for residential properties. So Economilloc understands their responsibility as a utility to minimize phosphorus discharge from their plant. And they've done that by automating ferric dosing using the ELISA analyzer. But they also recognize that wastewater is just one part of the problem. Agricultural runoff and stormwater play huge roles in watershed phosphorus loading. So that's why the OWPP brings together stakeholders from across the community: lake associations, MS4s, landowners, conservation districts, universities, consultants, all working together to reduce phosphorus at the source. So the key takeaway here is that Economilloc isn't just meeting permit limits, they're leading by example. By investing in real-time monitoring and automation at their plant, and by participating in upstream watershed initiatives, they're really tackling phosphorus pollution at every level. Now let's move on to another utility in Wisconsin, Fond du Lac Regional Wastewater Treatment Facility. Fond du Lac Regional Wastewater Treatment Plant and Resource Recovery Facility. Their name is a mouthful. This large utility treats about 8 to 10 mgd and has an effluent phosphorus limit of 0.6. The plant uses both enhanced biological phosphorus removal and chemical phosphorus removal to ensure that they consistently meet their effluent limit. The ELISA orthophosphate analyzer is installed at the aeration effluent to monitor biological performance and automate backup chemical dosing when necessary. So this is a look at the activated sludge train at Fond du Lac. There are 3 passes in this train, but shown are only pass 1 and pass 2. Pass 1 is this zone with no aeration. This zone is targeting anaerobic conditions for the PAOs to biologically remove phosphorus. This zone is controlled by a YSI ORP sensor to verify that the conditions are anoxic. Pass 2 is ammonia controlled. It's controlled with an ammonia IOC sensor to target the removal of nitrogen from the water. And pass 3, which you can't see here, is DO controlled. Now, prior to implementing the EBPR system, Fond du Lac did chemical phosphorus removal using an orthophosphate analyzer located at the effluent of their facility, same as Economilloc's setup. However, they didn't like this because it introduced a 3 to 4 hour lag from where the PO4 analyzer was reading and where chemicals were dosed. They wanted orthophosphate measurements, but they wanted them further upstream so that they could take immediate action and not catch phosphorus loads 3 to 4 hours after the fact. So that led them to purchasing an Alyza IQ PO4 analyzer and installing it outside directly in the aeration outlet channel to monitor PO4 concentrations from their activated sludge system in real time. This is where the Alyza PO4 analyzer is located. This concrete channel is the aeration outfall channel following pass through. The Alyza unit was installed last year, just as their EBPO system was going online. In this location, the Alyza serves a dual purpose. Now it monitors biological phosphorus performance, and it automates chemical dosing only when needed. The plant still uses the effluent are tied together in a dual control scheme. So if either one sees a PO4 level above 0.15 parts per million, then chemical dosing kicks on. This is a look at a SCADA trend from September 2024, showing Alyza PO4 in dark teal, effluent orthophosphate in light teal, and ferric pump response in orange. The control loop is using two orthophosphate analyzers with the same set point of 0.15 milligram per liter. So as effluent PO4 rises above 0.15, the system responds by ramping up ferric dosing. You can see the Alyza PO4 reading dips before the ferric pump hits its peak speed. Because ferric is dosed upstream at the analyzer, as ferric is added, it rapidly binds with soluble orthophosphate in that part of the system. The Alyza, which is installed shortly downstream, picks up this localized drop in PO4. But then the Alyza reading rises again temporarily, which can happen maybe because ferric is not fully mixed throughout the flow stream, or because incoming PO4 loads may still be entering the system faster than the chemical dose can compensate. Eventually, the ferric fully reacts and mixes throughout the system, and we see the Alyza PO4 drop again and stay low. Shortly after, the effluent PO4 drops as well, confirming the system-wide phosphorus removal. The Alyza analyzer is installed outdoors, exposed to Wisconsin's weather year-round, and it's continued to deliver reliable data in all conditions. The Alyza is rated for use in -4 to 104 degrees Fahrenheit. The analyzer is installed at the effluent of the aeration system, which allows operators to confirm biological phosphorus removal in real time. As long as orthophosphate levels stay low at that point, they know the PAOs are doing their job. And if they aren't, if PO4 levels start to rise, the system automatically triggers ferric dosing based on that data. So that ensures the plant only doses when it's actually needed instead of relying on some kind of fixed schedule. When I had visited this facility in December 2024, they had not needed to dose any chemicals for phosphorus removal since the SCADA trend we just took a look at, which was from September. So about 2 months without chemical phosphorus removal. So the key takeaway here is that the Alyza provides reliable outdoor performance. It gives operators confidence in their biological process, and it supports efficient chemical dosing when needed. All right, now let's move on to the final utility, Kewaskum Wastewater Treatment Plant. Kewaskum is a small utility treating just 0.4 mgd, but they discharge into a really impaired segment of the Milwaukee River, which is listed as impaired due to elevated TSS and phosphorus levels. They have a total phosphorus effluent limit of around 0.2 milligrams per liter. So despite being such a small utility, this plant manages limits that utilities 10 times its size do. For now, Kewaskum meets their current limits with chemical phosphorus removal. However, they have more stringent phosphorus limits to come that are near non-detect levels. So they have plant upgrades planned for 2028. They've been piloting tertiary filtration systems as well as different chemicals for phosphorus removal, such as rare earth minerals. The ELIZA analyzer currently automates chemical dosing at the plant, but it's also been used to help in the pilots of tertiary filtration. And it's installed at the final effluent of the treatment process. When the analyzer was first installed, the laboratory tech did some upfront testing of orthophosphate and total phosphorus for about a month to compare it to the analyzer to confirm its accuracy, and both matched really well. This graphic shows the SCADA control scheme for the 2 chemical feed pumps at Kewaskum. The feed pumps are based per liter. These graphs show orthophosphate concentrations from the ELIZA analyzer at Kewaskum during late November and early December 2024. Kewaskum uses a 0.2 milligram per liter set point to control ferric dosing. And what's clear from both the daily and weekly data is that the system is maintaining PO4 levels well below this set point, typically around 0.01 to 0.03 milligrams per liter. So Kewaskum is operating well below their permit limit and almost in the non-detect levels of phosphorus with only chemical removal. The control scheme is based off of influent plant flow, so ferric pumps are always running, and then ferric pumps speed up and provide more dosing if PO4 levels rise above 0.2 milligrams per liter in the effluent, which hasn't been the case, but it's still keeping PO4 well under control. In fact, they're likely overdosing chemicals based on setting the pumps on influent plant flow instead of solely on the orthophosphate concentration. At Kewaskum, the ELIZA is doing more than just monitoring and controlling chemical dosing. It's providing deeper insights into the entire treatment process. The plant is looking ahead to future upgrades in 2028, preparing to meet ultra-low phosphorus and TSS limits. To get ready, they piloted both rare earth chemical phosphorus minerals and a tertiary filtration system. The ELIZA has been instrumental in these pilots by giving operators real-time phosphorus data to evaluate performance. During one tertiary filter test, Supervisor Ben Propson allowed the PO4 levels to climb to 0.4 to 0.5 milligrams per liter intentionally to test how well the filter would perform under higher loads. The ELIZA was monitoring the influent to the tertiary filter, and Ben told us it tracked those levels perfectly, helping simulate realistic pilot conditions. The key takeaway from Kewaskum is that while this is a small plant with a small team, their leadership has made smart investments in quality instrumentation. These tools help them meet today's limits while also preparing for tomorrow's. As Ben put it, I sold my board on the idea of buying equipment now that helps us upgrade smarter later. And for a small utility like Kewaskum, that means setting up the plant and future operators for success. Ben shared that installing the analyzer helps bulletproof the system so the next person walking into the control room doesn't have to worry about it. To wrap things up, we've seen how phosphorus is essential to life, but when it goes unmanaged, it becomes one of the most disruptive pollutants in our waterways. Whether you're using chemical dosing, biological removal, or planning for future upgrades, real-time phosphorus data gives you the control and confidence to make better decisions, not just for compliance, but for efficiency and for sustainability. Online analyzers like the ELIZA make this possible. With only about an hour of maintenance per month, you can automate chemical dosing, verify biological performance, and optimize your process 24/7. And as we saw from the case studies in Wisconsin, from large facilities like Fond du Lac to small, high-performing plants like Kewaskum, smarter phosphorus monitoring is achievable, scalable, and impactful. So that's it. Thanks for listening. Copies of these case studies with more details will be available after the webinar. We also have a great phosphorus ebook, which details all of this educational phosphorus content that we will share. And if you're curious about how this might work at your facility, feel free to reach out to me over email. I'd love to help.